He has built teams, products, and startups of various scale. He reads Golang code on GitHub for fun. He leads all containers and cluster management technologies team at Uber. Please welcome Kiran Bondalapati.
Hello, everyone. Thank you so much. Thank you to JFrog for having me here, especially Shlomo and Ayala. And also, thanks a lot to the JFrog team for organizing such a great event. I want to talk a little bit about scale. Doing DevOps at scale, especially at Uber, is something that affects the whole DevOps workflows in different phases. And I want to go through some of the things that we had to go through in our journey. But first, let's talk about Uber as a business. Earlier this year, we completed our 8 billionth trip, and that's a cool animation that shows like from the 5 billion trip to the 8 billion trip. We have a great visualization team at Uber too, and we open source a lot of those technologies. We do 15 million trips per day. We are on 6 continents, 78 countries, and 600 plus cities. We have 75 million active monthly users, and more than 3 million active drivers on our platform. All of this business is supported by 16,000 employees worldwide with about 3,000 developers. That number might look a little big, but just to put it in contrast, you actually do not get fired for emailing all the developers at Uber. And also, we do have still weekly all hands where Dara shows up and talks about how the business is doing and how the technology we are building is working to solve a lot of the problems, transportation problems around the world. Talking a little bit about how Uber thinks of itself. Our philosophy, we call it bits plus atoms. Uber is building a technology platform that moves physical entities around the world. As an example, we started with people and cars. Now we have Uber Eats, which delivers food from the restaurants to your home. We also have Uber Freight, which started in Chicago, but now is moving loads of out of the country. We also have Uber Jump, which we've recently acquired, so you can actually use an electric bike around San Francisco, and we expect to roll it out around the world. And coming soon to a city near you, Uber Air. We believe this technology platform that we've built enables all of these moving of physical entities around the world. Why is this important? Why is this philosophy important? Compared to a lot of the scale that we see in much bigger companies around us, we are in a unique position that we're really moving physical entities using technology. What that means is when systems fail, when there are outages, that actually causes you to really miss events. It's not that your vacation photographs do not show up to all your followers. You actually cannot make it to your vacation. That really drives how we think of building systems, building applications, building DevOps workflows. What does DevOps look like at Uber? I'm going to take you through a little bit of a journey through each of these phases. I'm not going to do a deep dive into all of these, but give how scale affects all of these different phases of DevOps workflows. First, let's talk about what is that scale. We have thousands of microservices, triggering thousands of builds per day, more than 10,000 deployments each day of all of these microservices. We run more than 100,000 service containers per cluster. I want to contrast that with service containers with actually batch workloads that we also run on our platform, where we actually launch more than 1 million containers per day. Digging into what is this microservices composed of. Initially, Uber actually, as an application, was built by contractors as a PHP application. The product market fit was so good that what technology we used to build the application did not matter. But now, we made a bet on using Golang as our main platform. So over time, we've moved from Node.js to Go for our marketplace. Some of the core services that were built in Python are moving to Go. We do still have Python and Java on the data side, because as all of you know, a lot of the data infrastructure is built in Java. So we don't force languages on developers. We encourage them, and we could use Leo to encourage more of those people to move to Golang. Uber, about a couple of years ago, made a heavy bet on building everything in microservices. This is sort of a visualization of how our microservices looked like in March 2016. And this is how they look like today. It's beautiful, but it comes with a lot of complexity. That is a visualization of real-time traffic patterns of all of our microservices interacting with each other at Uber. What this brings is the microservices. The architecture actually enables Uber to run efficiently. As an example, when you dispatch a car, if you actually fail to calculate the ETA, the expected time of arrival, you can still take the ride. Just your ETA doesn't show up because it's completely done in a different microservice. Similarly, we also have how we calculate surge pricing based on the traffic and based on the amount of people requesting rides, also in a different microservice. That service is one where almost every customer Uber wants an outage, because when it has an outage, you get default pricing, no surge pricing. But at least you still make it to your destination. That's what is key. So microservices actually has paid off for us in a big way in being able to allow all the developers to iterate fast, build newer services, and build newer products. And like I talked about, a lot of different use cases. Uber Eats as a platform runs on very similar technologies as the rest of Uber. Once you have all of these code written into microservices, all of them trigger more than 4,000 builds per day. What does that mean? 3,000 developers, 4,000 builds per day, of about 3,000 microservices. The build times that people are sitting there and waiting for become the enemy of developer productivity. And similarly, the actual build sizes end up being the enemy of deployments. When we look at this scale, initially our build tool was based on Docker build. Like I said, we are heavily on microservices and containers. We had to use the forked version of Docker build just because of secrets management and credentials. But over time, we realized that it was holding us back. So we started building our own internal tooling, which actually builds without Docker. As all of you know, Docker images are mostly layers of tar files. We optimized how we build those layers, especially when you're building lots of microservices. What we also realized is instead of forcing developers to use different layers and reuse them across different groups, we actually enable developers to build their Docker files whichever way they want. But when building 3,000 microservices, we do a lot of caching of all of the intermediate layers that we build that can be shared across all of these developers. Now, we have this build engine already rolling out in production, and we expect to both write about it and also open source this tool very soon. Google also recently released a similar project, I think Koniki. We looked at it, and we realized that we started around the same time solving very similar problems, and we actually have solved a few more problems than the open source tool. So we'd really love to get the community feedback on it very soon. Now, once you have built this one, once you have built this tool, what does it mean to actual developer productivity? Here's an example of an image that actually took like 16 minutes, 44 seconds to build, and resulted in a 3 gig image. Once we use this tool, which optimizes all of these layers and then also uses all of this caching, we realize gains of more than twice as fast, and the image is almost 60% of the original size. This makes huge difference to the developer productivity when you're sitting when 3,000 developers are sitting there waiting for their builds to finish. Similarly, once you take this optimized builds, how do you deploy this across the whole clusters that we run? We are on multiple data centers and multiple clouds. So once we have that, we have our registries based on open source Docker registry and JFrog Artifactory for storing a lot of the artifacts and images. And we love JFrog Artifactory. It's been a great product for us. But once we start scaling these microservices, hundreds of microservices can get deployed at the same time, and they're all pulling thousands of images across multiple data centers. And like I said, cloud. Once you have this thing, we pretty soon realized that the original registry we started out did not scale. So we tried standard techniques, vertical scaling, throw more CPUs and memory at the problem. We tried caching. We tried horizontal scaling. But we realized pretty soon that the way Uber's business was growing and the way the microservices and the requirements were growing, we could not keep up with traditional technologies of scaling. So we had to use something else that internet taught us. What we do is we try to build systems which scale with the actual load. So we built a peer-to-peer distribution system for the images. So we do some horizontal scaling, but then we actually use all of the clusters around the world to actually distribute the images among themselves once they pull from some of them pull from the main registry. What this results in is much more efficient distribution of our images around the clusters. As an example, here's a visualization of a real image getting distributed around the cluster for a few hundred instances. It used to take minutes. Now it finishes in a few seconds. This drives the internal code name for this project is Kraken. We also expect to work on both writing about this and open sourcing it pretty soon. Once you've built all of these, the images are deployed on all of these clusters. All the services are running on, like I said, multiple data centers, on the cloud. What happens with efficiency? An important aspect of applications and microservices is all of these applications and microservices are sized or provisioned for peak traffic. Saturday nights, Halloween, Christmas Eve, New Year. Once you have all of these provisioning done for peak traffic, most of the rest of the time, the cluster actually is running at pretty low efficiency. We use Apache Mesos for our cluster management, and we actually have committers on our team committing back to Mesos to improve a lot of Mesos frameworks. When you're running at such low utilization, what can you do? One technique that we came up with is to combine guaranteed and revocable tasks on the same platform. As an example, Tier 0 services, which are really involved in dispatching cars to people, actually are always guaranteed resources. But we also take batch tasks, which are used to process payments in the background, which are used to calculate analytics. We take all of them, and we run them at a lower tier. And the idea is when the guaranteed tier tasks start peaking, start taking more traffic, we have real-time observation of what is going on in the cluster, and then we kill off these revocable tasks, which can be restarted in another location. That sounds great. That sounds like a natural thing to do when you have large clusters and you want utilization to go up. But an interesting thing happened when we rolled this out into production. We have such a large scale with multiple data centers. We still do want to test what happens when a full data center goes down. So we have high availability tests where we fail over one data center fully into another data center to cover all of the traffic within that one data center. This exercise actually triggered a cascading failure and outage on the revocable tasks, which still do some important business logic. So they don't like this to completely go out as long as we can handle the traffic. What we realized is when you switch over one data center traffic to another data center, there's a lot of scheduling that's happening, so there is a burst. And it's a scheduling burst more than actually traffic burst. And the scheduling burst results in revocable tasks getting killed, and now they're trying to get rescheduled, and that results in more cascading load on the scheduling, and that results in an outage. So what we realized is just by simply rate limiting how fast we schedule things and kill things, we can actually have the cluster utilization still up, but handle significant events like data center outages. How do we figure out what is going on in all of these situations? Like, what scheduler caused an issue, or if there's really outage, or we can't handle the traffic? We built an internal metrics platform called M3, also in Go. This currently has about 5 billion time series, and it's ingesting about 10 million metrics per second. And this was built to scale, and as we are scaling, there's something interesting that happens. We still have new microservices that get provisioned almost every day, and we still have New data centers, new clusters, new zones in clouds getting added every day into our infrastructure. We're also adding new metrics to measure more things. So there is constant change. So this metrics platform that is used to aggregate all the metrics, build some alerting rules so we actually get emailed or paged when there's high urgency events. What happens to this metrics platform? As you change things around in the system, people have to go in and manually add, remove, edit all of these alerting systems that we've built. We have a query language which is used to construct the alerts. Now, what we had to do to solve this problem was really build a rules-based alert generation. So people don't go in and write queries to build their alerts anymore. They actually write rules on the platform and what sort of alerts need to be generated and what type of metrics. We take these classes of rules, and adding a new data center is as simple as adding the data center code, and then the rules generator takes over, runs through all of these things, and it's actually based on a very simple Git-based post hook. So you check in your rules into Git, they can be reviewed. Once they land, the rule generation system kicks in. It picks up all of these changes, pushes all the new rules into the alerting system and the monitoring system, and all of the new high urgency, low urgency emails and PagerDuty hooks all get triggered. Once you have this thing, another aspect that we realized is a lot of the people, the developers writing the alerts, adding the metrics, writing these queries, are not the same people who are on call for all of these systems. Specifically, when you're going 24/7 around the world, we build systems and someone else is on call for them. So we actually do a lot of extensive analysis on measuring our on-call quality. What this really means is if there is an alert, how often is it firing? How often is it firing for real reasons? How often is it firing for spurious reasons? Are there runbooks to handle this? What does the on-call person who's handling this think of the runbooks? So the SRE organization, the on-call people, a lot of the developers actually go on call. That's the best way to really solve any problem with quality of your alerts, is to really put the developers on call. I want to take a step back. Instead of talking about how we do each of these things, look at the 30,000-foot view of what we think is the philosophy on what we're trying to address this scale. Our goal, I'm sure everyone's goal in this whole conference, is automate everything. So we try to do auto-provisioning, auto-deployment, auto-configuration, auto-scale applications, infrastructure, auto-update and upgrade, microservices, infrastructure agents, auto-detect failures at host level, at physical infrastructure level, at application level, traffic overloading. We try to separate out our health signals from liveliness signals. All of this results also in building systems which also auto-remedy themselves and auto-recover from failures. We build a lot of these automation systems. So when you're building these, one important question that we ask ourselves is, how do we design these systems? What scale do you design these systems for? Because scale drives Uber a lot more than maybe many other startups and many other companies. But the change in scale is much bigger than just the actual scale. So we are always thinking of how do we design for what scale do we build any of these automation systems? And the way to think of this question for us and for everyone out there is, how long does it take to build for 10x scale versus how long does it actually take for the business or the infrastructure to reach that scale? This multiplier actually could be different for many different companies. But if you change the multiplier to 2x, it might be the exact same question for you. We think of it as if it takes a week to build a tool or build an automation system that lasts a quarter, maybe it's not worth it. If it takes a month to build a system that lasts for a year, it's on the borderline. But if it takes to build a week to something that will last for a year, we actually go ahead and do it. We don't think of, will it last the second year? We actually go and rewrite it at the end of the year, maybe take a month then if needed, to build it for 2 years. That's the type of thinking that goes on every day when we're building all of these systems. What scale are we designing for? What scale do we think we get to? And both based on predictions And one thing that definitely has happened at Uber is we've blown through most of these predictions in the past. We're hoping to get better at this thing over time. When you design for this scale, what else happens? We build a system, and that system solves some problem, both automation, DevOps, tooling, all of these things. I call them as a system. It solves some problem. The engineer or the engineers or the team which built that system completely understand what's going on in that. But over time, as you're scaling, as you're building more systems, they have more complexity, they have more interconnection, they have more interactions, and the larger systems actually mean that any small change you do in any of these actually has a big impact. At the same time, to handle the building of all of these systems, your team grows, there's more people, and all of these people know less and less about each of the systems that are being built. So this is a very important aspect of scaling both systems and people, is every day, every engineer, this is true at Uber, this is true at many other companies, every engineer knows less and less about the bigger and bigger systems that they're building, and the changes that they're doing actually has more and more impact. We studied all the outages that happened at Uber, and what we realized is 1/2 of the outages happened due to a change in code. 1/4 of the remaining outages happened due to a change in config. So 3/4 of all of the changes cause all outages. There's a very simple, very simplistic view to look at this. Some people say, oh, code doesn't fail, people cause failures. People cause outages. Code doesn't cause outages. I think that's a very simplistic view. We have a very nuanced view. When we studied all of these things, our basic realization was that our understanding of the systems breaks down more often than the systems do. It's not us doing mistakes. We don't understand the systems that we're building, and that's what causes the outages. This is something that I actually take to heart every day, the whole team takes to heart, and this is not an easy thing to fix. You have to have better automation, better documentation, better specifications, better APIs. There's a lot of things we try to do to address this problem, but this is something that we had to deal with as we scale Uber. I want to leave you with that message and tell a little bit that we're actually solving a lot of interesting problems. All of these things that we talked about are something that we've solved in the very recent past. This is not something that we built like a year ago. All of these things, they're rolling out into production today, and we're already thinking about what is the next system to build by the time this rolls out into production. So we are hiring for many of these things. Thank you so much.